In this video, we will talk about the differential operator, the Dell operator, and how it can work on a scalar field to produce a vector and give us what we call the gradient. So this is our overview slide, which we'll spend about 5 minutes going over, and then we'll talk about each topic in more detail and with more examples. We will start with the Dell operator, which is notated with this upside down triangle, and in many places, as in your book, also with the bar on the top. In Cartesian coordinates, the Dell operator is equal to the ith basis vector multiplied by the partial derivative with respect to x sub I. So if x sub I, this is expanded, where x sub 1 is equal to x sub 2 is equal to y, and x sub 3 is equal to z. So that will give us the 3-tuple, or the triplet, partial derivative with respect to x, partial derivative with respect to y, and partial derivative with respect to z. We can take the Dell operator and act on a scalar field, that is, act on a function that produces a scalar, and then our Dell operator will then produce a vector. So here we have an example. Here phi is a scalar function, so it takes an x, y, z and produces a scalar. When we have the Dell operator operate on this scalar function, we get back a vector, and the vector is the partial derivative with respect to x, partial derivative with respect to y, and partial derivative with respect to z. An example is the electric field. It's equal to the negative gradient of the electric potential. We can also take the Dell operator and operate on a vector field. If we take the Dell operator and act on a vector field with the dot product, we produce a scalar, producing what we will call divergence. If we take the Dell operator acting on a vector field with the cross product, then we will produce a vector, what we call curl. Divergence and curl are two things that we will cover in our next video. After we introduce the Dell operator, we will take a look at the gradient, which is the Dell operator acting on a scalar field. So the vector, the gradient is a vector that describes at each point how the field changes with position. It points in the direction of greatest change, we'll talk about hill climbing, and therefore is perpendicular to any displacement that produces no change, a level curve, for example. We will develop a physical picture of the gradient. We'll work through this example to talk about, to calculate how the gradient will tell us how phi, our scalar field, is changing at a particular point when we walk in a particular direction. There will be other examples we go through as well. That wraps up our overview, so now we're ready to go into details about the Dell operator. As I had mentioned, the Dell operator is notated with this upside down triangle with the bar to indicate that it does represent a vector. And we define the Dell operator as the ith basis vector times the partial derivative with respect to x sub I. So expanding this out, the sum out, that would be the first basis vector times the partial derivative with respect to x1 plus the second basis vector times the partial derivative with respect to x2 plus the third basis vector times the partial derivative with respect to x3. And if x1, x2, x3 equals x, y, and z, we have d dx in the x direction, d dy in the y direction, and d dz in the z direction. So as a 3-tuple or a triplet, that would be d dx, d dy, d dz. When we have the Dell operator acting on a scalar field, we produce a vector. So I've copied this equation over here. So I have the Dell operator operating on a function phi that takes a vector and maps it to a scalar. And by definition, then what we're going to have is e to the I, then we're going to have the partial derivative of our phi with respect to dxi. So expanding that out again, and I drop the x1, x2, x3, but you just have to remember it is a function dependent on x, y, and z of a vector. That's e1 d phi dx1 plus e2 d phi dx2 plus e3 d phi dx3, and then written as a triplet, and I feel like this is the most concise way of saying it, it's d phi dx, d phi dy, and d phi dz. In other words, it's your phi, your function, taken a partial derivative with respect to each of the variables x, y, and z. The example is the electric field is equal to the negative gradient of the electric potential, and we will do an example of this. In our next video, we will talk about divergence and curl, and these are both the Dell operator operating on a vector field rather than a scalar field as we're covering in this video. So we can act on a vector field with the dot product, and since it's with the dot product, we'll produce a scalar called divergence, or we can act on a vector field with a cross product, and since the cross product produces a vector, it's this operator will produce a vector, and that's called the curl. So the rest of this video focuses on the gradient. What we will see is first that the gradient is a vector that describes how the field changes with position at each point. 2, it points in the direction of greatest change. And so in the hill climbing analogy, if you think of your three-dimensional map as kind of a topographical map, I got this image from REI. So let's say you have a topographical map. This is the 3D image. This is the level curves. And the idea of the level curve, we talked about that in one of our previous videos, is these are the paths along your mountain or hill that if you follow this path, you'll stay at the same height. So it's where your elevation does not change. And here you see there's a level curve where the elevation stays at 1440 feet or whatever it is. Yeah, it's probably feet. Anyway, so the idea of a gradient now is if you have your map and you think about it as a topographical map, the gradient for every point will point in the direction that where the elevation is changing the fastest. So it'll be the direction of steepest ascent or descent. In other words, it's, ascent if you're in the positive direction, descent if you're in the negative direction. And remember, you don't have to literally be hill climbing. It doesn't have to be the REI map. It could be any function that represents, say, maybe cost, in which case the gradient will point in the direction where you can increase or decrease your cost the fastest. The last point of the gradient is that it is perpendicular to any displacement that produces no change. For example, level curves. Level curves, since the rate of change is 0 and the gradient is where the rate of change is the greatest, you expect these two things to be perpendicular to each other. That means if you have a mapping of the level curves, if you just draw a path that's perpendicular to all the level curves, you just have to hit each level curve perpendicular, that would give you the gradient or the path of fastest change. And now we want to justify this claim that the gradient vector describes how the field changes with each position and also how it points in the direction of greatest change. I cleared some space just to give us some room, and I started with the definition of gradient here, and I moved it here. And I'm going to dot both sides of this equation with dr, a small change in position. I can also write this change in position as a change in position in the x direction, y direction, and z direction. What I have then on the left-hand side is my del of phi, and I went ahead and dropped the x1, x2, x3, but just remember it's a function that takes a vector and produces a scalar. So I have my del of phi dotted with dr is equal to, and now I rearrange some of these terms, my d of xj, e sub j, dotted with e sub I, d phi of dx of I. And now, because e sub I dotted with e sub j is equal to 0 unless I equals j, that means, and when I equals j, it's equal to 1, that means all that's left is my d sub x sub j, d phi, dx of I, but I has to equal to j, so we get dx of I, d phi, dx of I. I probably just should have done this all in one step. When we look at this, this represents the change in phi when we have this small change in direction. So it's the total differential change in phi due to a differential change of position dr. It might be easier to see this in vector notation, so when we expand this out, this here becomes d phi. So the change in phi is equal to our gradient vector dot dr, our little change in position. Looking at this vector notation, this talks about the change in phi. And what it says is it's a dot product. So one thing we know about dot product, one, it's equal to 0 when things are perpendicular. So it's minimized, or it actually has no change. It's equal to 0 when the gradient is perpendicular to our direction of movement. So when we move perpendicular to the gradient, there's no change in our phi. However, when we move in the same direction as the gradient, that's when we maximize our change in phi. And this is how we get our claim: the gradient points in the direction of greatest change and is perpendicular to any displacement that produces no change, a level curve, for example. Next, we're going to develop a physical picture of the gradient, and we're going to use kind of a simpler function than like the electric potential, because that's a more complicated one. We're going to use this phi of xy is equal to negative xy. Notice how phi takes a two-dimensional vector and maps it into a scalar. We can choose phi to map a three-dimensional or an n-dimensional vector and map it into a scalar, but we chose a two-dimensional vector just to make it easy on ourselves because we want a graph. And the graph of phi of xy, so it has two variables, and then you solve for z, or phi in this example, but z on the z-axis is a three-dimensional graph. As we had discussed in an earlier video, in order to get some easy visualization of a three-dimensional graph, we often look at the level curves. In other words, we set phi equal to a constant. We see what those graphs look like, and they'll be two-dimensional graphs. So looking at our level curves, we're going to set phi equal to some constants, and I chose some small constants: 1, -1, 2, -2, 1/2, -1/2, and then I looked at what my level curves will look like. So when phi is equal to 1, I have 1 is equal to minus xy, which means that y is equal to -1 over x. When phi is equal to -1, I have -1 equals minus xy, which means y is equal to 1 over x. When phi is equal to 2, I get y equals -2 over x, phi is equal to -2, y is equal to 2 over x, phi is equal to 1/2, y is equal to -1 over 2x, and -1/2 y is equal to 1 over 2x. And here I have graphed my level curves. In black, I have when phi is equal to -1/2, which gives me the graph of y equals 1 over 2x. So I have this graph and then the other half over here. And then in yellow, I have phi equals -1, which gives me y equals 1 over x. So that's this graph, which you're probably familiar with. And this one on this side, I did phi equals -2, phi equals 1/2, phi equals 1. And you can see my graph here. To get a sense of what it looks like in 3 dimensions, essentially think of raising this black curve to a height of, or lowering it to a height of -1/2. This yellow curve lowers to a height of -1/2, while the green goes to -1/2. So these are all sort of decreasing down. And over here on this side, we're going to raise this curve to 1/2, and we're going to raise this blue curve to 1. And you might remember from vector calculus, when we have this sort of look, the three-dimensional graph is a saddle, but in this class we won't emphasize drawing the three-dimensional graph. Now that I have phi, I can look at taking the gradient, and that's d dx of my function, d dy of my function, and partial derivative with respect to x will give me -y, and partial derivative with respect to y, I need a negative in here, will give me a -x, which is -y in the e direction and -x in the y direction. Now we can use our gradient function, so we can calculate the change in phi if we are standing at the point 1, 2, and we move an infinitesimal amount, dr, in the positive x direction. And here we have the calculation. The change in phi is equal to the gradient dotted with our change in direction. So our gradient evaluated at the point 1, 2, dotted with d and with dr, and our direction vector is only in the x direction. And I feel like this notation is kind of strange. It's awkward for me. So I just kind of wrote it out. So r is equal to our r vector is equal to r times the x component plus r times the y component plus r times the z component. So dr is dr times the x, dr times the y component, dr times the z component. So if we're only in the x direction, that means the y and z component are 0. So we get dr e to the x plus 0, and then just written out in Cartesian coordinates, that's just dr 0, 0. And if we're in 2 dimensions, that means we have dr 0. And that's what we have over here, dr 0. So then also plugging in our gradient of phi at 1, 2. So at the point x equals 1, y equals 2, we can plug that in over here. I'm just going to plug it in over here. First we have negative y, which is negative 2, and we have negative x, which is negative 1, and I keep dropping this negative, dotted with dr 0. That's just negative 2 dr. And what that physical interpretation means is our phi decreases by 2 units for every unit moved in the x direction. If instead we're at the point 3, 4 and move an infinitesimal amount dr at a 45-degree angle with respect to the x-axis, we have our same formula. Our d phi, our change in phi, is equal to the gradient at 3, 4 dotted with, and this is our direction vector. To get our direction vector, we have this angle 45 degrees from the x-axis, so we can represent that direction vector, or start to get the direction vector. Well, the direction vector is equal to the vector 1, 1. However, we need to normalize it so it's unit length. So our vector 1, 1 normalized is, the length is 1 over square root of 2, 1, 1. So what we have here is our dr over square root of 2 in the x direction in the y direction. Putting that all together, our gradient at 3, 4, well, that's equal to negative y, negative x, and I keep dropping this x. So that will be negative 4, negative 3, dotted with 1 over square root of 2, 1 over square root of 2. Again, this is our vector at the 45-degree angle, that's unit length, and that will give us negative 7 over square root of 2 dr. As a physics major, you need to know when using the gradient to generate a vector field, we usually add a negative side to the definition. So for example, the electric field is generated from the electrostatic potential by E is equal to the negative gradient. And using this convention, moving against the field lines increases phi. Looking at our previous example where phi is equal to negative xy, that would mean our negative gradient is now equal to negative, and then the partial derivative with respect to x is negative y, partial derivative with respect to y is negative x, so that gives us yx, or y in the e direction and x in the y direction. We can now plot this vector field using the techniques we talked about in the video 2.1 when we talked about representing scalar and vector fields. To represent this vector field, what we would do is at each point in our xy plane, we would associate a vector. And for this function, my negative gradient of phi of 0.11 would equal to negative 1, which is just equal to 1, 1. So that means my vector 1, 1 looks like this. And then we would translate this vector up to the point 1, 1. We would go through all the points in the xy plane and then fill them with all these vectors. And we said eventually it just gets cluttered with a lot of vectors. So there are different ways of handling that. And in 2.1, we said that a vector field then will be drawn by constructing lines which are tangent to the field at every point in space. And by convention, the density of these field lines indicates the magnitude of the field, while the arrows show its direction. So this is the convention we're going to use, or that we decided to use. And since the field lines are tangent to the electric field, the tangent of the electric field is the slope, the rise over run, which is equal to EY divided by e to the x. And that is going to give us then the tangent line, which is dy dx, or the change in y over x is tangent, is equal to EY over EX, where EX is the partial derivative of phi with respect to x, and EY is the partial derivative of phi with respect to y. In r phi here, d phi with respect to x, derivative with respect to x is negative y, d phi with respect to y is negative x, so dy dx is equal to our negative x over negative y, which gives us dy dx is equal to xy. Cross multiplying then, I get dy times y is equal to dx times x. I integrate both sides and I get 1/2 y squared, 1/2 x squared. The halves cancel out. I get y squared plus x squared plus c. So what I have is x squared minus y squared equals c. That's what my field lines look like. And again, I graph my level curves. This is where x squared minus y squared equals 1. That's in blue. X squared minus y squared equals 2. That's in yellow. I have my other two level curves here. This next slide, I think this is so cool. Anyway, so this graph here are the field lines for the gradient. This is where there's the steepest or fastest change. This graph here, we had done a few slides ago when we were doing level curves of phi. So these are fastest change, these are no change. But look what happens when we move this graph over. What you see are the level curves are perpendicular to the gradient field lines. So that's kind of cool. And that's also one of the things I was telling you. If you have the level curves, you can kind of graph out the gradient by drawing lines that are perpendicular, and vice versa. I have one more example. I have the scalar function f of xyz is equal to x squared e to the minus yz. So this is my phi. Compute the rate of change at 1, 0, 0, at the point 1, 0, 0, and the direction of the unit vector v equals 1 over square root of 3, 1 over square root of 3, 1 over square root of 3. So that's our first question. Our second question is, in what direction from 1, 0, 0 does f of xyz increase the fastest? For the first question, compute the rate of change of f at 1, 0, 0 in the direction of the unit vector, this unit vector v. So the rate of change, that's given to us by the gradient, and we plug in, the gradient is a scalar function dependent on x, y, z, so we plug this in and we get a rate of change. If we want it in a particular direction, then we dot it with that vector. And this is the formula we had used before, where we had the change in phi, or in phi, and in this case our phi is this f of x, y, z, so it's equal to df, which is equal to the gradient of f evaluated at x, y, z, dotted in our change of direction. Plugging in some of the numbers, we have the gradient of f evaluated at 1, 0, 0, dotted with our direction vector, 1 over square root of 3, 1 over square root of 3, 1 over square root of 3. You notice this direction is the same as 1, 1, 1, but we have to use a unit vector. And the reason why we have to use a unit vector is we don't want to disturb the scalar quantity. In other words, we don't want to scale it based on our direction. So we need our direction to be normalized. So we preserve the direction of the vector without disturbing the scalar value of our gradient. So if someone hasn't normalized this direction vector, in other words, if you had been given the vector for direction as 1, 1, 1, you would have to normalize it. If you did not, you'll get the wrong answer. The next thing we need to do is start taking the gradient of our function f. So here is our function f. The gradient is the partial derivative with respect to f, that's x squared e to the minus yz with respect to x, the partial derivative of x squared e to the minus yz with respect to y, and the partial derivative of x squared e to the minus yz with respect to z, again evaluated at 1, 0, 0, dotted with the direction vector. Taking the partial derivative of our x squared e to the minus yz with respect to x, that just gives us 2x e to the minus yz. The partial derivative with respect to y, so that's going to bring down the z, so we have the negative z, so we have minus x squared z e to the minus yz. Partial derivative with respect to z is going to bring down the negative y, so we have negative x squared y e to the minus yz evaluated at 1, 0, 0, dotted with our direction. Now evaluating this vector here at the point 1, 0, 0, plugging in 1 for 2, 0 for y, 0 for z, this gives us 1, so we have 2 times 1, which is just 2. Here we have an x squared, we have a z, which is equal to 0, so this coordinate goes to 0. And also because the y is equal to 0, this coordinate goes to 0. So we have 2, 0, 0 dotted with our direction, which gives us 2 over square root of 3. And this here is the rate of change of f at 1, 0, 0 in the direction of the unit vector v, 1 over square root of 3, 1 square root of 3, 1 square root of 3. To answer my second question, in which direction from 1, 0, 0 does f of x, y, z increase the fastest? So that's just the gradient. The gradient is the direction of fastest change. So the fastest change is equal to the gradient, which I've rewritten here, evaluated at 1, 0, 0. So we plug in and we get 2, 0, 0. So the direction, well, you could say the direction is 2, 0, 0, or you could just simply say it's in the x direction, or the I hat direction, or the e to the x direction. Looking at our overview sheet, we've just done this example here, and one thing we need to note is to calculate the change over a finite path, where the gradient changes as we move from one point to another, we need to use a line integral, and we use this formula here. That concludes the material for this video. To review what we discussed, we talked about the Dell operator, which is notated with this upside down triangle, and it is a vector, so we put a bar on top. In Cartesian coordinates, our Dell operator essentially becomes the partial derivative with respect to x, partial derivative with respect to y, and partial derivative with respect to z. We talked about how the Dell operator could act on a scalar field to produce a vector, and that was called the gradient. And we have this formula here. So the gradient of the scalar function is equal to the partial derivative with respect to x of phi, the partial derivative of phi with respect to y, and the partial derivative of phi with respect to z. And our example was the electric field is equal to the negative gradient of the electric potential. We talked about divergence and curl, and that's when we use the Dell operator acting on a vector field. And we can operate using a dot product to give us divergence, or a cross product to give us curl. And we'll talk more about divergence and curl in our next video. We did some detailed analysis of the gradient, and we found that a gradient vector describes at each point how the field changes with position, and it points in the direction of greatest change, and also is perpendicular to any displacement that produces no change, for example, a level curve. Last, we developed a physical picture of the gradient, and we used this kind of simpler phi to illustrate this, and we took the partial derivative, which is the derivative with respect to x of phi, derivative with respect to y of phi, and then we got, this is also a negative, so what we got was negative y, negative x. And then we did different drawings of the level curve of each of these. We did the exercise of calculating the change of phi if we are at 1, 2, and move an infinitesimal amount, dr, in the positive x direction. You can see this calculation here. And last, we also noted to calculate the change over a finite path where the gradient changes as we move from point to point, we need to use a line integral. So that's it for this video. Well, as I said, our next video will talk about divergence and curl. Thank you for watching.